Hi everybody, we're here again in the Mantle TP Calcs workbook, and in this video we're going to we're going to slide over here to column T, the operative KD, iron magnesium exchange coefficient. So for a little bit of background, in an earlier video, we explained that this input here, the liquid compositions that you input in these columns and the oxygen fugacity that you set in these columns here, are going to affect the predicted force-right component for the olivine that is here. So this here is the olivine composition that we would expect to have in equilibrium with the liquid that is entered in this same row. So the question one needs to ask is that value commensurate with what you would expect for the mantle source of whatever it is you're analyzing or attempting to estimate the mantle potential temperature for? So for example, here in this first row, this liquid, given the conditions that we've stated, the conditions being the oxygen fugacity and the calculated pressure based on silica activity, yields a force-right content that is predicted to be 92.22. So maybe you think that is too high or too low. Well, one of the avenues in which we would analyze and change that value is through our assumption of the KD. So now we're coming back over here. So just to show you how these are linked, this is operative KD. This is the iron magnesium exchange coefficient through which all the calculations that depend on that value, they will be linked to this cell. So if we change this, this is linked to column AM8 over here, but you don't have to use that equation. We could just type in a value. If you don't like 0.35 and if you don't like any of the equations, we can just put in 0.30. Let's say you think that's the operative KD, and if you look over here, you could see the FO value increased from 92.2 to 93.18. And if we move in the opposite direction to something higher, let's say 0.37, then we would expect that it would go down a little bit, and there it did. It went down to 91.71. So you can play a game to pick an operative KD that would give you the value of force-right that you think is best. But in the nominal way the spreadsheet is set up, the default setting is to link it over here to these equations that are in columns AI to AN, or excuse me, AK to AN, specifically column AM. So what's in column AM? We're going to take a look at this equation here. This is from Paterka 2016, an American mineralogist, and it is an equation that predicts the KD value from pressure and composition, presuming that oxygen fugacity is known and that we are calculating some total fraction of ferrous iron based on the amount of ferric iron that is in turn based on the oxygen fugacity. So there's a chain of reasoning here. If you want to bypass models for estimating Fe203 contents, you can instead use one of the models here. So for example, in this case here, in AK, this is a model that depends on pressure and composition, but then it takes the oxygen fugacity directly as a variable. So you could choose this one or this one over here. They're very different because they're looking at the iron-magnesium exchange coefficient in different ways. They're both counting for oxygen fugacity, but in this case here, it's oxygen fugacity, but still assuming that all the iron is expressed as iron FeO total, whereas here we're going to assume an oxygen fugacity, but allow the calculations to move forward to calculate an Fe3 plus Fe2 plus ratio, which is done elsewhere in the sheet. Where, you ask? Way over here to the right. If we're not spinning around enough for you, we'll spin around even further. Out in these columns, way out here in the distance. Here we go. We're using, it's not really Paterka 2015, it's actually 2016, but it was 2015 when I was writing these equations. These equations here take your input values and then calculate ferric-ferrous ratios and then a predicted iron magnesium ratio for olivine based on an operative KD. So that is all based on inputting a liquid with a known amount of iron. You don't have to input Fe2O3, it's going to be calculated over in that distant part of the spreadsheet based on this FO2. All right, so that's a lot of information. Let's go back to the nuts and bolts of how we use this operative KD. For the most part, you might just want to leave it set and allow it to be making use of the predicted value over here in column AM. You can change it to take this value or just put in a fixed value if you like. But here's another way to think about it, and here's the way I often use the spreadsheet. Let's say, as an example, that we think the Hawaiian mantle has a mantle olivine composition of 90.5. So let's say that is the olivine composition that we think that all mantle equilibrated liquids would have seen. So if that's the olivine composition, then we know that this composition is not right. Now, of course, it's not right. I'm using something from, this is actually a Greenland example, but for the purposes of this video, I've set it up as a Hawaiian case. What can we do? Well, we could do a couple of things. We could take this composition here, we'll hit edit copy, and we're going to move to this spreadsheet here, parental magma calculation. And gray is input, so I'm going to go to edit paste special, just the values. We don't want to carry over the formulas. So here's the composition as our starting liquid, and we can add or subtract an olivine composition of anything we like. It could be FO87 olivine. We could pick any target we like. We've already got 90.5 entered, but you can put in 92 or 91 or 89.9, anything you like. We'll move it back to 90.5. And then you can pick an operative KD. This is not linked to any other spreadsheet. This spreadsheet is entirely self-contained. And so here's an iron magnesium ratio of 0.33. It was 0.346. I think in the other spreadsheets, we'll just use that. This composition here, we'll move it back to FO88 as a function of oxides. It's here, so if you have this composition, this four-strike composition of olivine, this is what the weight percent oxides will be. This here is the liquid that would be in equilibrium with this olivine, but only after we adjust these cells over here. So we have to tell Excel to do some numerical approximations, and we're going to do it this way. The way it's set up is we want this cell to be 0 by adjusting this cell here. And the easiest way to do that is Tools Goal Seek. So we'll go to Tools Goal Seek. We want this cell A31 to be 0 by changing this cell A28. And as I hit OK, you'll see the numbers down here change. And they change a little bit, not too much. And then we could take these values, copy, go back to Calc P Iterative, and then do edit, paste special, again, values only. We don't want to copy the formulas. And now we have that new composition entered here. And it should be now predicting FO 90.5, correct? Well, no, it's actually 92.37. What happened? Well, here's the thing that's very important. We are assuming in the spreadsheet that all the iron is FeO. There's no accounting of ferric-ferrous ratios or oxygen fugacity in this sheet. So if we come back to Calc P Iterative, we can set an oxygen fugacity where all of the iron is going to be FeO. The nominal case is that we're taking nickel-nickel oxide right at the nickel-nickel oxide buffer. You can go back to one of our earlier videos to take a look at that. But if we go, let's say, 20 units below the nickel-nickel oxide buffer, I'll enter negative 20 here. That is very reducing. We'll have a little bit of ferric iron, but not much. And we should get pretty close to 90.5. And we do, we get 90.47. So within rounding error, probably certainly within the error of knowing what the actual mantle olivine composition is, we've done a good job of approximating it. But you might say, well, I don't want the case of nickel-nickel oxide minus 20. I want something that is equilibrated right at nickel-nickel oxide. Well, what can we do then? Well, I'm going to show you that. We'll just end this video showing you how I go about approaching these kinds of calculations. We can insert a row, and then I'm going to grab all of row 8 and then just do a fill down. So now I have an exact copy of that row. But for this label, I'm just going to enter a number, and that number will be the fraction of liquid in a mixing calculation. So if I have an olivine composition, I'll come back to parental magma calculation. I'll take this row. Notice we have nominal 0 values for titanium, aluminum, manganese, calcium, etc. You can fill in numbers for those if you like, if you have something that is a little more precise. But for a nominal value, it's really just the silicon, magnesium, and iron that's really going to make a difference here. So we'll work with that. We will set up an equation that is a mixing equation, where here in row number 9, I'll take a mixture of this liquid in row 8, multiplied by the fraction of liquid that I think we have, plus 1 minus the liquid amount. Wrong. I want to take 1 minus this, multiplied by the olivine, so that's the fraction of olivine. And I want to fill right so I can apply this mixing equation to all of the oxides, not just silica. So when I fill right, I want to hold that fraction fixed. And so everywhere there's an A for column A, I'm going to put a $sign to hold that fixed. So now I can fill right. And we have a mixing equation where we take a mixture of this liquid here and that olivine. Now, if I have 100% liquid, and this is my liquid, then of course these two will be identical. But I can have, let's say, 90% liquid, 0.9. So now I'm adding olivine to it, which allows me to drop the silica and increases the MgO. And of course, the four-strike content in row 9 will be changed. I've added some olivine to it, so I've increased the four-strike content. I've made the liquid more magnesium, so it's going to be in equilibrium with a more magnesium-rich, more four-strike-rich olivine. If we're aiming for 90.5, we want to go in the opposite direction. So instead of 0.9, you can consider it this a subtractive function by going something greater than 0.9. To make the reference a little bit easier, I'm just going to take this cell here and make it equal to this four-strike content, and then I can just find a value here, let's try 1.2. Oh, that's too high, 1.15. Now we're getting closer, 1.16. Oh, we get 90.5 right on the dot. So this is just a linear mixture, a mechanical mixture in this case, because this value is greater than 1. I'm actually subtracting olivine rather than adding it. It really doesn't matter how you do the algebra. It's all falling on a mixing line, so it's all the same thing. Now I have a liquid here that is in equilibrium with 90.5. Remember, this is equal to cell 18.9. So we'll go over to cell 18.9. And there it is, right at the value that I'm expecting. Now that I have a liquid that is truly in equilibrium with what I expect for the mantle, I can now emphasize the estimates here. I'll just put them all in red. So here are what I consider to be the more valid estimates of pressure and mantle potential temperature, and a more valid estimate of error as well, based on those inputs. And so this is how we use the KD function. The other trick that you might want to do, you might be tempted to use goal seek, but I'll introduce you to one of the problems. In a small spreadsheet like this, where there are not a lot of calculations that are highly connected, then goal seek works very well when we're looking at these cells here. But there are a lot of iterative calculations in this spreadsheet here that link pressure and fugacity and temperature and composition. So in theory, we should be able to use goal seek. Let me put this back to, I don't know, 0.9 or something, or 0.8. Doesn't matter. It's not at the value that we want for this fellow here to be 90.5. So we could try tools goal seek. and let this cell be equal to 90.5 by changing this cell here. I could take the original 18.9, it really shouldn't matter, they're all linked. But as you could see, the system is going crazy, and I'm just gonna, I was gonna hit cancel. Yeah, even if I hit cancel, yeah, if I hit cancel, it goes back to normal. It has trouble finding a solution, and I think part of the problem here is that we just have one iterative calculation too many. It could be that we're just bumping into a circularity by adding in that extra variable for a weight fraction in a mixing calculation. So I usually do these by hand, but in just the way I've shown you. It might even be easier if you have to do a lot of these to take an entire column and just let this whole column be equal to AT. We could just type it in. So AT8, and then we could fill down, and then we could set up, instead of labels here, we can have an extra column where we just have estimates, and we can do a bunch of mixing calculations over here. So I just give you that as a warning. I've had that failure happen many, many times, and I thought it might save you a little bit of time rather than trying to find out by destroying the spreadsheet on your own. Okay, I hope that's helpful, and we'll have another couple of other videos that look at how to go a little bit deeper into controlling some of the input variables into the spreadsheet.